When we work out, the goal is always to move more weight. For every training goal, the method to reach is by lifting more and eventually progressing. With this overarching factor, many people sacrifice their form and execution just to move more mass. However, does this increase in weight really represent progression? To answer this question, we must define progression. Progression in all forms involves muscles gaining the ability to exert more force on the bones that they act upon. So, isn't it reasonable to say that the muscles must exert more force with more weight? Well, in the context of human joints, it isn't this simple. Let's take a closer look. This is the upper arm. The muscle that we are looking at right now is the brachialis, the main muscle that acts when the elbow joint flexes, or when the elbow's angle decreases. Every muscle has two connection points to bone. The tendons at either end of the muscle connect to the bones that will be pulled together. The bones in this case are the humerus and the ulna. From the middle of the humerus, the brachialis attaches to the top of the ulna and pulls the ulna up about the elbow joint when contracted. This is the humerus, this is the ulna, and this is the elbow joint. And we can see that the brachialis attaches to the middle of the humerus and to the top of the ulna. And when contracted, it pulls the ulna up about the elbow joint. Pretty simple, right? It's kind of like a pulley. Let's see this in the context of a bicep curl. With this movement specifically, we are seeing a type 3 lever in action. Levers are simple machines that include an effort, a load, and a fulcrum. In the case of a bicep curl, the effort is the upwards pulling force applied by the brachialis as it contracts. The load is the dumbbell, and the fulcrum is the elbow joint. This is a type 3 lever because the effort is in between the fulcrum and the load. The most important concept to touch on can now be introduced: moment arms. A moment arm is the distance between the fulcrum and the line, perpendicular to the force of direction. Sometimes, such as in this case with a bicep curl, there are many forces. The different forces in this scenario are the downwards force of gravity acting upon the dumbbell, or the load, and the upwards force exerted on the ulna by the brachialis, or the effort. So this would be the downwards force of gravity acting upon the dumbbell, and this would be the upwards force exerted on the ulna by the brachialis. Since there are two different forces, two different moment arms are formed, and they are the external and internal moment arms. So we can see here that this is the line of resistance for the load, or the dumbbell, and this is the line of resistance for the effort, or the muscle. And this is the axis of rotation, which is always parallel to the direction of the lines of resistance. And we can see that the internal moment arm is the distance between the axis of rotation and the line of resistance. So this is always smaller, which is why it's called the internal moment arm. And then we have the external moment arm, which is the distance between the axis of rotation again and the line of resistance for the load. So this is always longer. And we can see that when you hold a dumbbell, the distance between the ulna's insertion of the brachialis and the elbow itself, it's a very tiny distance. And then the distance between the elbow and the dumbbell that you hold, this is a much longer distance, so that's why it's called the external and the internal moment arm. It's also called the internal moment arm because it's inside the body. So why do moment arms matter though? Well, torque, or the rotational force a joint experiences, explains how much work the muscle must really do to move a load. And the equation goes: the load force multiplied by the external moment arm length is equal to the torque. And the same torque is also equal to the effort force multiplied by the internal moment arm length. So as we can see here, this would be the dumbbell, and the force of gravity acting upon the dumbbell multiplied by the external moment arm length is equal to the torque that the joint experiences at this moment in time, hence the name moment arm. And that same torque at this moment in time is also equal to the amount of force exerted by the brachialis, or the effort force, and the distance of the internal moment arm. So obviously the internal moment arm is far shorter than the external moment arm. So this means that with any load, the external moment arm is going to be greater, meaning that the internal moment arm on the other side of the equation is going to be smaller. So the muscle has to exert a huge amount of force to accommodate for the high load and the high external moment arm. What this equation means is that the weight moved is really only half of the equation in determining how much growth the muscle will experience. The external moment arm, or the distance between the weight and the joint perpendicular to the resistance, is the other half. And the best way to maximize the external moment arm is to use correct form and controlled execution of a movement. So since both the internal and external moment arms are on the same joints, the torque that the external moment arm creates is the same amount of torque that the internal arm creates. And since the internal arm is less than the external arm, like I said, the distance from the elbow to the brachialis insertion is far less than the distance from the elbow to the dumbbell. The effort force, or the force exerted directly by the muscle at any given moment, must increase to a great extent to compensate. Therefore, we can say that the downwards force of gravity exerted on the dumbbell creates a torque to which the upwards force of the brachialis contraction must increase. All of this may seem pretty complex, but let's look at it in the context of some more exercises. So that was the barbell squat, one of the most basic movements in all of lifting. Let's find the moment arms. There are two major joints that the muscles act upon: the hip and the knee joint. Looking at the knee joint specifically, we can see that the axis of rotation is simply the vertical line that crosses the knee and starts from the floor. So it starts from the floor, crosses the knee right here. It's the line kind of to the right, and yeah, that would be the axis of rotation. And we can also see that it coincides with the effort's line of resistance, and pretty much coincides with the low's line of resistance as well. And the low's line of resistance, which is basically the force of gravity exerted on the barbell when you squat, that is always going to be directly over the feet, because if it goes forward, the person is going to fall forward. If it goes backwards, the squatter is going to fall backwards. So just to keep balance, it always stays above the feet. So the line slightly to the left, that's the low's line of resistance. And we can see that all of the moment arms, the distance between all of these lines, it's pretty much negligible. You can barely make out the difference in these lines. They're basically all in the same location. So we can say that in the standing part of the squat, the load's line of resistance, the effort's line of resistance, and the axis of rotation, they're all basically in the same spot. So there is no moment arm. And this means that there's very little torque acting upon the joint. So, conforming to the stated definition of a moment arm, the external moment arm of the knee increases as the lifter descends into the squat. And this is because, as the lifter descends, the knees move further forward, as shown in this diagram. So, we can see that the axis of rotation moves further apart from the efforts line of resistance and the loads line of resistance, which, like I said before, always stays on top of the knee. And the efforts line of resistance in this case, that's the point on the tibia where the quadricep tendon inserts. So pretty much anyone who has ever done a weighted squat before would know that the hardest part of a squat is the bottom, which is also called the hole. And the physics-based explanation for that is that the knee joint's moment arm is longest at the bottom of the squat, and it therefore experiences the most torque in the hole, as shown in this figure right here. The same exact stuff goes for the hip joint. As the squatter descends, the hips move further and further back, creating a longer moment arm. By the equation we touched on earlier, the torque experienced at each joint per the external moment arm is equal to the torque per the internal moment arm. So by isolating the effort force in the equation, we can find the exact amount of force at any given moment that the muscles, in this case are the quadriceps and the glutes, must exert on the bones that they're attached to. Let's touch on the progression question as previously. In the squat example, the most common type of form deterioration is simply not going down far enough. Obviously, not everyone has full range of motion, but people with full range of motion still do half squats just because they're easier. That is, using 100 pounds on a full squat would be harder than using 100 pounds on a half squat, and this is because of the shorter maximum moment arm. So often, some people load extra weight onto the bar during a half squat, and this is what we call ego lifting. If someone who half squats a certain weight tried a full squat with the same weight, they likely couldn't get past the hole. People who half squat and want effective results should instead ditch the inappropriate weight, practice full range of motion with a lower weight, and work up to a sufficient working weight after form has been fixed. Let's put moment arms in the context of biomechanics. Take me, for example. I have very long femurs relative to my height, and this creates some differences in the squat compared to someone with shorter femurs. Someone with a shorter femur would technically have to travel less relative distance to achieve the depth standard, which is when the femurs are parallel to the ground. Someone with shorter femurs would also have smaller moment arms for the simple reason that their limbs are shorter. Furthermore, a common pattern in Olympic and professional squatters is that most of the high-ranked competitors have shorter femurs. We notice a pattern in depth standards too, that the standard is at or slightly past the sticking point of the lift. For the squat, the sticking point is a hole, and the depth standard is to reach the hole. And for the bench press, the sticking point is slightly above the chest, and the standard is to touch the chest. In Olympic and professional bench pressing, many high-level lifters arch their backs to a great degree. What this action does is elevate the chest, therefore reducing the total range of motion and decreasing the length of the chest's maximum moment arm. So, what can we conclude from this? Well, form is very important. If we want to progress, our muscles must be placed in conditions where they're required to exert more force than they're used to. By disregarding form, the muscles don't have to exert as much force due to shorter moment arms. With shorter moment arms, there's more room for more weight, so joints end up experiencing the same torque, just in shorter range of motion. Not only is this harmful to the joint, but it means that the muscles will experience less growth due to certain biological processes related to the stretch reflex and the length-tension relationship. In conclusion, solidify your form and work up to a difficult weight that can still be moved with good technique. This is the best tried and true way to grow. Application of physics in everyday activities can often lead to new open doors.